Hi, my name is Zohair Kachwala, and I'm very excited to talk about my work today, which is robust and efficient matching of local knowledge graphs to improve structure and semantic similarity. We call our algorithm Rematch. I'm a PhD student at Indiana University, and I'm very grateful to my collaborators and great faculty, Jason An, Haven Kwak, and Filippo Menza, who's also my advisor. If you'd like to get straight to this paper, you can use this QR code. This work has largely been funded by Indiana University's Observatory on Social Media. So, what is Rematch designed for? Rematch is an algorithm to compare abstract meaning representations. So, what are abstract meaning representations? Here is an example to give you a taste of it. So, on the left hand side, you see a piece of text which is talking about how Mr. Mueller was given the role of special counsel by the Justice Department to lead its investigation into alleged Russian interference in last year's US election. A fairly complex sentence. You can see on the right hand side is an AMR representing the sentence. You can see that the key actors in this sentence have been represented by nodes, and the relationships between them has been captured by edges. So you can see that abstract meaning representation is a label graph representation for language. To better understand and break down the different components of an AMR, let's go through a simpler example. So here we have a sentence which is talking about he did not cut the apple with a knife. The first class of components of an AMR are called instances. These are like the core semantic features of sentence. In this case, we can see that he, apple, and knife, as well as the verb cut, form the key components and are represented in the color blue and are representing the nodes in this graph. The next and the second class of components are called attributes. These are edges which connect instances to constant nodes. In this case, you can see that the negation to the verb cut has been represented by this edge polarity connected to this negative sign. The third and the last set of components are called relations. These are the edges between instances. In this example, you can see that he is connected to cut via the edge arg0, which basically means that he is the agent of the verb cut. Similarly, apple is the patient of the verb cut and knife is the instrument for the verb cut. Now that we've understood the different components of an abstract meaning representation, you might ask, why should one use this framework? And the reason is that language is different from meaning. On the left hand side, you see a lot of sentences that talk about a young child riding a horse. They are said in different words, but they actually mean the same thing. So ideally, we want a representation that regardless of the sentence and regardless of the words used, it should be just one representation, which is this AMR. And similarly, if there is a sentence that is slightly different, we would want a representation that is slightly different as the one on the bottom. Now we want to create machines that can automatically extract abstract meaning representations from sentences. And to do this, we have to use ground truth created by linguists as the one on top. And then we need to compare the AMRs created by the machine with the one at the bottom. And the task to compare these two AMRs is called AMR matching. This is what Rematch is designed for. And as you can see, one property that an AMR matching algorithm should have is it should be able to detect the subtle differences in structure between AMRs, like this node person, which is different between these two AMRs. Another property that we desire from abstract meaning representations is that it should be able to capture the differences in meaning between AMRs. On the left hand side, you see these two AMRs which mean the same thing. So an AMR matching metric should return a high score of 1 for them, whereas the one on the bottom means something different. So an AMR matching algorithm should reflect that by returning a low score of 0.1 for both. And these are exactly the properties that we will evaluate Rematch as well as other AMR metrics. Structural consistency to measure how well they reflect the differences in the graphical structure of two AMR. Semantic consistency to check how well they reflect the differences in meaning between these two AMRs. And efficiency to check how fast they are. Label graph matching is a very computationally expensive problem, and we want a metric that can do this quickly so that it can scale to large AMRs. Now let's talk about a method Rematch. The first step in Rematch is to generate AMR motives. For the sentence, Helen's talking to Maya about movies. We have this AMR on the left, which includes the three components that we described, instances in blue, attributes in orange, and relations in red. Rematch uses these components to create respective graph features that we refer to as motives. So first, we create a motif from the attributes. Uh, an attribute motif is nothing but a tuple of the attribute edge label and the constant node. So in this case, we have op1 Helen and op1 Maya. Next, we have the instance motif. This is a nested motif, so it combines two things. It first starts off with the instance label. In this case, we have name. And then if there is an attribute linked to that instance, then we also include the attribute motif generated before in the previous step. So name includes op1 Maya and name op1 Helen. In the case of instances that do not have any attributes linked to them, it's simply the instance label itself. As you might notice, there are two person instances on the left-hand side, but there's only one instance motif. Since this is a set of motifs, there are no duplicates. And the last are relation motifs. Again, this is a nested motif which combines three things. It combines the source instance motif, the relation edge label, and the target instance motif. So the source instance motif is person, which is basically the one that we generated in the previous step. Then comes the relation edge label name. Then comes the target instance motif, which also includes the attribute motif attached to name. So this is simply from the previous steps. So now we have relation motifs for these two relations, and then similarly for the other three relations that do not have instance motifs with attributes is simply the instance label, the relation label, and the instance label. So this is the process of generating AMR motifs. It starts with attribute motifs, and then you create nested instance motifs, which includes the attribute motifs, and then we create the relation motifs, which includes the instance motifs in the previous step. So now coming to the second step of Rematch, which is a similarity calculation. So let's say we have these two sentences. Helen is talking to Maya about movies, and Helen did not talk to Maya about politics. We have these two AMRs representing these two sentences. And now Rematch creates a motif set for each one of them, set A and set B. And the second step and the last step for calculating similarity is basically calculating a Jacquard index for these two sets. Jacquard index, for those who might not know, is simply taking the intersection of the two sets over the union. So in this case, there are 7 AMR motifs in common between these two sets, and there are 20 motifs in total between these two sets. So we have a similarity score of 0.35. So as you can see, Rematch has this two-step, very simple, very straightforward process. So now let's evaluate Rematch against other AMR metrics. The first one is structural consistency. Unfortunately, there is no benchmark for AMR structural consistency evaluation, so we had to create our own. The way we did that is we took the AMR 3.0 corpus, which is basically a set of AMRs created by linguists, and then we started rewiring edges between them. So on the left-hand side, you can see a very simple small AMR, which is talking about the boy wants football. And we rewire the edges by swapping boy with football. And now the AMR becomes something like this on the right-hand side, which basically means the football wants boy. We keep rewiring edges when it's possible. And the score, the ground truth similarity score for these two pair of rewired AMRs uses the original graph and the randomized graph, and it's basically the relative change in the number of edges between them. So in this case, there are two edges, and we have rewired both of them. So the E represents the total number of edges, and R prime represents the rewired edges. So in this case, since we have rewired all of the edges, the similarity between these two AMRs should be 0. This is how we create a synthetic benchmark for evaluating AMR metrics on structural consistency. And these are the results. We call this benchmark randomized AMR for rewired edges, also rare. And the score is basically the Spearman correlation between the AMR metric scores and the ground truth annotated scores for all pairs of AMRs. As you can see, S-match performs the best, and Rematch is the second best with a score of 95.32. The next property that we evaluate AMR metrics on is semantic consistency. To do this, We use two standard benchmarks, STS and SICK-R. These benchmarks consist of pairs of sentences annotated by humans. The scores range from 1 to 5. So 5 is for sentences that mean the same thing, as is the first example, and 1 is when the two sentences mean completely different things. So our goal is to use these human scores as a way to evaluate the AMR metrics on semantic consistency. The way we do this comparison is we first take these two pairs of sentences, we parse AMRs from them, and then we use an AMR metric to compute the similarity between those two AMRs. Now, naturally, we can compare the AMR metric score with the original human score. And here are the results. These scores represent the Spearman correlation between the scores of AMR metrics and the ground truth semantic similarity, which is basically the human scores, across all pairs of sentences in these two benchmarks. We use 4 state-of-the-art parsers to mitigate any biases, and we see that Rematch performs well across both benchmarks and for all parsers. The last property that we want to evaluate for AMR metrics is efficiency. And here are the results. These are the results for a random sample of 500,000 AMR pairs, and we use all the metrics to record the total time taken, the total RAM used. We find that Rematch takes only 51 seconds and only 0.2 gigabytes of memory. This is 5 times faster than the next fastest metric, which is SemBlue. And when we evaluate the scaling of the complexity, we find that Rematch is linear. This is a log-log plot. On the x-axis, we have the average size of AMR pairs going from the smallest average size to the largest average size logarithmically. And on the y-axis, we have the runtime growing logarithmic as well. So what we find is that Rematch scales linearly with the size of AMRs. So do some other algorithms like SemBlue and WLK, but Rematch is the fastest. Some other algorithms like S-Match and S2-Match scale polynomially as with the growing size of AMRs. Finally, time for some takeaways. Rematch, our algorithm, is second best at structural consistency. It is the best at semantic consistency, and it is 5 times faster than the next most efficient AMR metric. Rematch also shows how AMR parsers have actually been encoding semantics better than previously estimated. If you would like to read our paper, access my code, or have any questions, please feel free to use this QR code. You should find all the details available on that link. Thank you so much.